Okay, in question 4, we've got a truck and a trailer question. Well, let's set the whole system up and put on the forces they've indicated. So there's the system redrawn with all of the forces in yellow and the acceleration in blue. We've got a pulling force of 7400, a resistive force of the car of 2R, and another resistive force of just the trailer of R. The tension in the tow rope is 2400, and we're going along with an acceleration of a meters per second squared. So let's have a look at part A. We're supposed to find the value of A. Well, if we consider the whole system, we've got a pulling force of 7400 newtons. We've got a total resistive force of 3R. The tension in the cable doesn't really matter because there's an equal and opposite force of 2400. So as far as the system is concerned, this balances itself out. So let's apply F equals ma in the direction of the acceleration. The balance of the forces going forward is 7400, and the forces opposing that motion, 3R, is equal to the mass, which is 1600 of the system, and the acceleration A. So that effectively is equation 1, and that's for the whole system. So I can apply F equals ma to either of the elements of this system separately now. Let's do the trailer. Looking at the trailer, the force pulling it along is 2400. The resistive force, a single R, is equal to its mass, which is 400, and the acceleration is the same. So this is equation 2, and this is for the trailer. We've got two simultaneous equations. We need to eliminate R. So the best way is to multiply equation 2 by 3. So 7200 minus 3R is equal to 1200A. So 1 take away 2 dashed, 7400 minus 7200 is 200. The R's cancel, and this is equal to 1600 minus 1200, which is 400A. So therefore A equals a half. And we're in meters per second squared. Now in part B, the rope between the car and the trailer has now been exchanged for a rope with mass, and the acceleration of the car is now found to be A1. State how the value of A1 compares with the value of A. Well, if the car and the trailer conditions remain the same, the whole system has more mass. So if the whole system has more mass, and F remains the same, the acceleration will be less. And that's it, really. And then part C. State one limitation of the model used for the resistance to motion of the car. Now, the motion of the car was modelled as a force pulling backwards of 2R. Now, this is a constant. But this is unlikely to be true in the real world because as the car increases in speed, the resistance, the air resistance and all sorts of other things, bearings and what have you of the car will increase. So you just have to write that down. And I've put that the resistance to motion Rn is unlikely to be constant. And those are the answers to parts B and C.